Let me tell you about one of the most intriguing discoveries in modern planetary science, a finding that suggests our solar system was not always as we see it today, that it once contained more planets than it now possesses, and that some catastrophic event removed one or more worlds from our cosmic neighborhood. Scientists have accumulated evidence that strongly indicates our solar system is missing a planet, an entire world that should be here but is not. Something destroyed it. This phrase captures the implication of the evidence we will examine. The absence is not random. The missing planet did not simply fail to form. Something occurred, a catastrophic event, a violent rearrangement, an act of cosmic destruction that eliminated a planet that should have existed. The traces of this event remain scattered through our solar system, telling a story we are only now learning to read. I want to take you through this discovery because understanding why scientists believe our solar system is missing a planet requires appreciating the patterns of planetary formation, the gaps in our cosmic neighborhood, and the evidence that points toward a violent past involving worlds that no longer exist. Let me start with what we know about how planets form. Planetary formation is one of the most active areas of astronomical research. Over the past few decades, observations of young stellar systems and increasingly sophisticated computer simulations have revealed how planets emerge from the disks of gas and dust that surround newborn stars. The process begins with a protoplanetary disk, a rotating cloud of material around a young star containing the raw materials from which planets will form. Within this disk, dust grains collide and stick together, gradually building up larger objects. The growth proceeds through several stages. Micrometer-sized grains become millimeter pebbles, pebbles become kilometer-sized planetesimals, planetesimals collide and merge into planetary embryos, and embryos eventually grow into full planets. This process is not uniform throughout the disk. Different regions produce different kinds of planets. Close to the star, where temperatures are high, only refractory materials, silicates and metals, can condense into solids. This produces rocky planets like Mercury, Venus, Earth, and Mars. Farther from the star, beyond what astronomers call the snow line, water and other volatiles can freeze into ice. The additional solid material allows plants to grow much larger, and they can then accrete hydrogen and helium gas from the disk. This produces gas giants like Jupiter and Saturn. Beyond the gas giants, ice giants like Uranus and Neptune form. These planets have less hydrogen and helium than Jupiter and Saturn, but more than the rocky planets with substantial amounts of water, ammonia, and methane. This picture explains the basic architecture of our solar system. Rocky planets close to the sun, gas giants in the middle, ice giants farther out, with smaller bodies, asteroids, and Kuiper belt objects filling specific zones. But the picture also makes predictions about which planets should form, where they should form, and how many should exist. When we compare these predictions to what we actually observe, discrepancies emerge. Some of these discrepancies suggest that our solar system once contained more planets than it does today. Now let me describe the most prominent gap in our solar system. If you look at the orbits of the planets, you notice something unusual. Mercury orbits at about 0.4 astronomical units from the Sunday, Venus at 0.7 AU, Earth at 1 AU, Mars at 1.5 AU. Then there is a large gap before Jupiter at 5.2 AU. This gap between Mars and Jupiter is where the asteroid belt resides. The asteroid belt contains millions of objects, but their combined mass is less than that of Earth's moon. This is far less material than would be expected to occupy this region of the solar system. Various patterns in planetary spacing, including the Titius-Bode law, an empirical relationship that suggests planets should be spaced at specific intervals from the Sun, predicted that a planet should exist between Mars and Jupiter. When astronomers in the 18th and 19th centuries searched this region, they found not a planet but the asteroid belt. The first asteroid, Ceres, was discovered by Giuseppe Piazzi in 1801. It was initially classified as a planet, but later reclassified when many more objects were discovered in similar orbits. The accumulating evidence revealed not a missing planet, but a belt of small bodies. But why is there a belt of small bodies instead of a planet? Two main hypotheses have been proposed. The first hypothesis is that a planet once existed in this region, but was destroyed. The asteroid belt would then represent the debris from this destruction. Various names have been given to this hypothetical destroyed planet Phaeton in some accounts, drawing on Greek mythology. The second hypothesis is that no planet ever formed in this region because Jupiter's gravitational influence prevented planetesimals from accreting into a planet. Jupiter, being so massive, would have stirred up the orbits of nearby planetesimals, causing them to collide at high speeds and shatter rather than merge. Modern astronomy has largely favored the second hypothesis, that the asteroid belt is composed of leftover building blocks that never assembled into a planet rather than the remains of a destroyed one. The total mass in the belt is too small to represent a destroyed planet. Even adding the mass that has been depleted from the region over billions of years, the total falls short of a planet-sized body. But the broader question remains: even if the asteroid belt itself is not the remains of a destroyed planet, this does not exclude the possibility that other planets once existed in our solar system and were destroyed. The asteroid belt might just be one piece of evidence in a larger pattern. Now let me describe more direct evidence for missing planets. Several lines of evidence suggest that the early solar system contained more planets than it does today. The NICE model and the Grand Tack hypothesis describe scenarios in which the giant planets move significantly from their original orbits, sometimes in dramatic ways. According to these models, the orbits of Jupiter, Saturn, Uranus, and Neptune were initially closer together and changed over time due to gravitational interactions with each other and with the surrounding disk of planetesimals. In some versions of these models, the rearrangement of giant planet orbits would have been dynamically chaotic. To match the current configuration of the solar system, simulations often require the presence of an additional ice giant, a fifth giant planet that was eventually ejected from the solar system during this chaotic phase. This hypothesis, called the fifth giant planet or Planet V hypothesis, though this name is also used for other hypothetical planets, is supported by detailed dynamical simulations. When researchers run simulations of the early solar system with only the 4 giant planets we observe today, they often fail to reproduce key features of our actual solar system. Adding a fifth giant planet, which is then ejected, improves the match significantly. What happened to this ejected planet? If the hypothesis is correct, it was flung out of the solar system by gravitational interactions with the other giant planets, particularly Jupiter. It would now be wandering through interstellar space, no longer bound to the Sunday. This is not destruction in the sense of being torn apart, but it is removal from our solar system. From our perspective, the planet is missing, gone, ejected, lost to the void between stars. Another line of evidence comes from studies of meteorites and the composition of solar system bodies. Some meteorites show signs of having come from a parent body that was once larger and was subsequently broken apart. Iron meteorites, in particular, suggest that they originated from the cores of differentiated bodies, objects large enough to have separated into a metallic core and a rocky mantle. For a body to differentiate into a core and mantle, it must be substantial, at least the size of a small planet or large asteroid. The number of distinct iron meteorite groups, each apparently from a different parent body, suggests that the early solar system contained many such differentiated bodies. Most of these bodies no longer exist. They were destroyed by collisions, leaving only the iron cores as meteorites. This evidence does not directly indicate a missing planet, but it does suggest a violent early solar system in which many protoplanets and planetesimals were destroyed. A third line of evidence involves the structure of the Kuiper belt and the orbits of distant trans-Neptunian objects. Some of these objects have orbits that are difficult to explain without invoking gravitational perturbations from a massive body. This has led to the Planet 9 hypothesis, the proposal that a substantial planet orbits in the outer solar system at distances of several hundred astronomical units. If Planet 9 exists, it represents the opposite of a missing planet, a hidden planet rather than a destroyed one. But the dynamical arguments are intriguing. The orbits of distant Kuiper belt objects show clustering that suggests a massive perturber, and various researchers have proposed that Planet 9 might be a former giant planet core that was ejected to its current distant orbit during the early dynamical instability. Now let me describe what catastrophic events could destroy a planet. If our solar system has lost planets, what events could be responsible? Several mechanisms have been proposed. Gravitational ejection is the most commonly proposed mechanism. When multiple giant planets are in close proximity, their mutual gravitational interactions can lead to chaotic behavior. In some configurations, one planet can transfer momentum to another, with one being pushed inward toward the sun and the other being pushed outward, potentially out of the solar system entirely. This mechanism does not destroy a planet in the sense of breaking it apart, but it removes the planet from the solar system. The ejected planet becomes a rogue planet wandering through interstellar space. Estimates suggest that the galaxy contains a vast number of rogue planets, possibly more rogue planets than stars. Many of these rogues were originally bound to stars, but were ejected during the dynamical chaos of early planetary system evolution. Our solar system likely contributed some of these rogues. Collisional destruction is another possibility. If two large bodies collide at sufficient speed, they can be partially or completely disrupted. The collision that formed Earth's moon, in which a Mars-sized body called Theia collided with the proto-Earth, is the most famous example. This collision destroyed Theia as a coherent body and left only a fraction of its material to form Earth and the Moon. If similar collisions occurred elsewhere in the early solar system, they could have destroyed planets or protoplanets. The asteroid belt and the diversity of meteorite compositions provide some evidence for such collisional history. Tidal disruption by the sun could destroy a planet that passed too close. If a planet's orbit is perturbed so that it approaches the sun within the sun's tidal disruption radius, the planet would be torn apart by tidal forces. The debris would be partially captured by the sun and partially ejected. This mechanism is not common in the current solar system. Planets are far from the sun and their orbits are stable. But during the dynamical chaos of the early solar system, some planets might have been thrown into orbits that brought them too close to the sunday. Stellar disruption could destroy a planet through interactions with other stars. The sun formed in a stellar cluster with thousands of other stars nearby. Close encounters with these stars could have perturbed planetary orbits, in some cases destabilizing them and leading to collisions or ejections. After the cluster dispersed, the sun's gravitational neighborhood became less crowded and stellar encounters became rare. But during the cluster phase, they would have been frequent and potentially disruptive. Engulfment by the sun is another possible fate. If a planet's orbit decays sufficiently through tidal interactions, drag from the protoplanetary disk, or other mechanisms, it could spiral into the sun and be destroyed. Some hot Jupiters and other planetary systems may meet this fate. Planets in our own system may have done so in the past. Now, let me describe the specific evidence for a destroyed inner planet. While the fifth giant planet hypothesis concerns the outer solar system, Other evidence suggests that destruction events may have occurred in the inner solar system as well. Mercury is the smallest of the rocky planets and has some unusual properties. It has an extraordinarily large iron core relative to its size, about 60% of its mass, compared to about 30% for Earth. Various explanations have been proposed for this anomaly, including the possibility that Mercury was once a larger planet that had its outer layers stripped away by a massive collision. If Mercury experienced such a collision, the material from its mantle and crust would have been ejected into space. Some of this material would have fallen back, some would have been lost to the sun or to other planets. The result would be the iron-rich planet we see today. The collision would not have destroyed Mercury entirely, but it would represent significant alteration. A larger pre-collision Mercury, plus the material that was stripped away, would constitute more material than the current Mercury. In some sense, a planet was destroyed, or at least drastically reduced. Other inner solar system anomalies have been proposed as evidence of past destruction. The relatively small size of Mars compared to Earth and Venus has been attributed to dynamical effects from migrating giant planets, but it could also be explained by Mars having lost mass through collisions or by another planet having interfered with its accretion. The peculiar properties of certain meteorites suggest formation from parent bodies that no longer exist. Iron meteorites from at least 60 distinct parent bodies have been identified, indicating that many differentiated bodies existed in the early solar system but have since been destroyed. Now let me describe what American scientists have contributed to this understanding. American researchers have played central roles in developing our understanding of how planets form, evolve, and sometimes disappear. The Southwest Research Institute in Colorado has been a hub for dynamical studies of the early solar system. Researchers there, including Hal Levison and others, developed the Nice model and its variants, which provide the strongest case for an ejected fifth giant planet. NASA's Goddard Space Flight Center and Jet Propulsion Laboratory contribute to studies of small bodies in the solar system. The Lucy mission, launched in 2021, is exploring Jupiter's Trojan asteroids, objects in stable orbits ahead of and behind Jupiter that may preserve information about the early solar system. The OSIRIS-REx mission returned samples from the asteroid Bennu in 2023, providing direct material from a primitive body. American universities, including MIT, Caltech, Harvard, and others, have contributed theoretical and observational studies of planetary formation and dynamical evolution. Researchers at Caltech, including Mike Brown and Konstantin Batygin, developed the Planet 9 hypothesis based on the observed clustering of distant trans-Neptunian objects. NASA's exoplanet program has revealed the diversity of planetary systems around other stars, providing context for understanding our own. Many exoplanet systems show evidence of dynamical instability, planet migration, and planet loss features that may also characterize the early history of our solar system. The cross-disciplinary nature of this research, combining dynamics, geochemistry, observational astronomy, and planetary science, reflects the complexity of reconstructing events that occurred billions of years ago. Now let me describe the timeline of these events. When did our solar system lose planets? The answer depends on which planets and which mechanisms. The earliest events occurred during the formation of the solar system itself, about 4.5 billion years ago. During this period, the solar nebula was still present and many planetesimals and protoplanets existed. Collisions were common and many protoplanets were destroyed by impacts. Some material was incorporated into the surviving planets. Some was scattered into the asteroid belt or beyond. Some fell into the sundae. The moon-forming impact occurred about 4.5 billion years ago during this early phase. This impact destroyed Theia, the body that collided with the proto-Earth, but its material was largely incorporated into Earth and the Moon. From one perspective, a planet was destroyed. From another, two bodies merged. The late heavy bombardment, a period of intense impact activity, may have occurred about 4 billion years ago. During this period, the inner solar system was bombarded by objects from the outer solar system, possibly triggered by the dynamical instability that ejected the fifth giant planet. If the NICE model is correct, the ejection of the fifth giant planet occurred during this same general time frame, several hundred million years after solar system formation. The exact timing is debated, but it likely occurred between about 4.4 and 3.9 billion years ago. Since then, the solar system has been relatively stable. Major dynamical changes have ceased. Planetary orbits have settled into their current configurations. The destruction of planets, if it occurred, happened in the distant past. This means that the missing planet we are discussing, or planets, if multiple are missing, has been gone for billions of years. The evidence we see today is fossil evidence, traces of events that occurred when our solar system was young. Now let me describe what we can learn from these missing planets. The possibility that our solar system has lost planets has implications beyond the specific history of our system. First, it tells us that planetary systems are dynamic. They are not static collections of planets in fixed orbits. They evolve over time, sometimes dramatically. Planets can migrate, collide, be ejected, or be destroyed. Our solar system today is the result of billions of years of evolution from very different initial conditions. Second, it suggests that the planets that exist now are selected. They are the survivors of dynamical processes that eliminated others. The properties of surviving planets, their orbits, masses, compositions, reflect not just initial conditions, but also the dynamical history that selected them. Third, it implies that other planetary systems may have similar histories. If our solar system lost planets, other systems likely did too. The exoplanet systems we observe today are also selected populations, the planets that survived the dynamical processes of their early evolution. Fourth, it raises questions about habitability. If planets can be destroyed or ejected, then habitable planets are also at risk. The conditions that allowed Earth to remain in a stable orbit in the habitable zone may be exceptional. Many potentially habitable planets in other systems may have been lost. Fifth, it provides constraints on planetary formation theories. Any successful theory must explain not just the planets we see, but also the planets we infer were lost. The patterns of survival and loss tell us about the underlying processes. Now let me describe what the missing planet might have been like. If we accept that our solar system likely had a fifth giant planet that was ejected, what was this planet like? Based on dynamical simulations, the most likely properties are mass, comparable to Uranus or Neptune, perhaps 10 to 20 Earth masses. This range fits the dynamical requirements massive enough to participate in the instability and be ejected, but not so massive as to disrupt the entire system. Composition, similar to Uranus and Neptune, with a rocky, icy core surrounded by hydrogen, helium, and ices like water, methane, and ammonia. This composition is consistent with formation in the outer solar system beyond the snow line. Original orbit between Saturn and Uranus, or in a similar region. The exact location is uncertain, but it must have been in a position to participate in the dynamical instability that rearranged the outer solar system. Final fate, ejected from the solar system. The planet would now be wandering through interstellar space, no longer bound to any star. It would be extremely cold, with no heat source other than its internal energy from formation, which would have largely dissipated over billions of years. This hypothetical planet sometimes called Planet V, or simply the ejected giant, would have been a substantial world. Its loss represents the removal of a significant amount of mass and complexity from our solar system. If we could find this planet, we could learn much about the history of our solar system. But finding a rogue planet in interstellar space is extraordinarily difficult. Such planets emit virtually no light. They can be detected only through gravitational lensing or other indirect methods. The specific planet ejected from our solar system might be impossible to identify. Even if we detect rogue planets, we cannot easily determine which star they came from. In part 2, I want to explore the evidence for planet destruction more deeply, examine what processes could have caused it, and consider what these events imply for the broader story of our solar system's formation and evolution. So we've established that multiple lines of evidence point to our solar system having once contained more planets than it does today. A fifth giant planet ejected during early dynamical chaos, possibly a larger pre-collision Mercury parent bodies of meteorites that no longer exist, and other indications of a more populated early solar system. We've examined the catastrophic mechanisms that could have destroyed or ejected these worlds. Now I want to explore this evidence more deeply. What specifically tells us that planets were destroyed? What chemical and dynamical fingerprints have these lost worlds left behind? And what do these traces reveal about the violent past of our cosmic neighborhood? Let me begin by examining the asteroid belt as a record of past events. The asteroid belt occupies the region between Mars and Jupiter, roughly 2 to 3.3 astronomical units from the Sun. It contains millions of objects ranging from dust grains to dwarf planets like Ceres. The total mass of the belt is small, about 4% of the Moon's mass, but the diversity of objects within it tells a complex story. Asteroids are not all the same. They are classified into different types based on their composition and spectral properties. The main classes include C-type asteroids, carbonaceous, containing carbon and water-bearing minerals, S-type asteroids, silicaceous, composed of silicates and metals, M-type asteroids, metallic, with high iron and nickel content, and various other types. The distribution of these types throughout the asteroid belt is not random. C-type asteroids dominate the outer regions of the belt. S-type asteroids are more common in the inner regions. M-type asteroids are interspersed throughout. This distribution suggests that asteroids formed in different regions and have different histories. But this distribution also suggests something more disturbing. The metallic M-type asteroids are particularly interesting. They are believed to be the cores of former protoplanets' bodies that grew large enough to differentiate into a metallic core and rocky mantle, but whose mantle was subsequently stripped away. For a body to differentiate, it must be substantial, typically at least 100 kilometers in diameter, often much larger. The differentiation process involves the heavier elements, mainly iron and nickel, sinking to the center, while lighter materials remain at the surface. This produces a layered structure with a metallic core, a rocky mantle, and possibly a crust. If we observe an asteroid that appears to be pure metal, an M-type asteroid, it is likely the exposed core of a former differentiated body. The mantle and crust have been removed, leaving only the iron core behind. How does this happen? The most plausible mechanism is catastrophic collision. If a differentiated protoplanet experiences a sufficiently energetic impact, its outer layers can be blasted away while the dense metallic core survives. The result is a metallic asteroid, the remnant of a destroyed protoplanet. The number of distinct iron meteorite groups identified in our collection suggests that at least 60 different parent bodies were destroyed in this manner. Each group of meteorites shows distinct chemical and isotopic signatures, indicating that they originated from different parent bodies. The implication is striking. At least 60 differentiated protoplanets once existed in the inner solar system but have been destroyed. These were not full planets. The iron meteorite parent bodies are estimated to have been a few hundred kilometers in diameter, much smaller than Mercury. But they were substantial bodies, larger than most current asteroids. They represent a population of intermediate-sized objects that existed in the early solar system and has largely been eliminated. Their destruction was not random. The pattern of meteorite types, the distribution of M-type asteroids, and the gaps in the asteroid belt all suggest that something systematically eliminated these bodies. The most likely culprits are gravitational perturbations from Jupiter and dynamical effects from migrating giant planets, but the details remain incomplete. Now let me examine the chemical evidence in more detail. Meteorites are extraordinary records of solar system history. They contain materials that have remained essentially unchanged since the formation of the solar system 4.6 billion years ago, providing direct samples of the materials that built the planets. Different types of meteorites tell different parts of the story. Chondrites are the most primitive meteorites. They contain chondrules, small spherical grains that solidified from molten droplets in the solar nebula embedded in a matrix of fine-grained material. Chondrites have never been melted or differentiated. They preserve the original composition of the materials from which planets formed. The composition of chondrites tells us about the initial conditions of the solar system. Different chondrite classes have different chemical and isotopic signatures reflecting formation in different regions of the protoplanetary disk. By studying chondrites, we can reconstruct the chemical and physical conditions in the early solar system. Chondrites are meteorites that have been melted and differentiated. They come from parent bodies that grew large enough to develop layered structures. Different chondrite classes represent different parts of these bodies: crustal materials, mantle materials, and various intermediate types. The HED meteorites, Howardites, Eucrites, and Diogenites are believed to come from the asteroid Vesta, the second largest asteroid in the main belt. Vesta is a differentiated body with a metallic core, rocky mantle, and basaltic crust. The HED meteorites represent samples of different layers of Vesta. Vesta is interesting because it appears to be an intact, differentiated protoplanet. Many of its siblings, other differentiated bodies, were destroyed, but Vesta survived. Studying Vesta gives us a glimpse of what the destroyed bodies might have been like. Iron meteorites, as mentioned, come from the metallic cores of differentiated bodies. They contain primarily iron and nickel, with various trace elements that distinguish different groups. The compositional diversity of iron meteorites indicates that they came from many different parent bodies. Some iron meteorites contain inclusions of silicate, material pieces of the rocky mantle of their parent bodies that were trapped within the metallic core. By studying these inclusions, we can learn about both the core and mantle of bodies that no longer exist. Stony iron meteorites, including pallasites and mesositerites, are intermediate types containing both silicate and metallic components. Pallasites, with their distinctive olivine crystals embedded in iron-nickel metal, are believed to come from the core-mantle boundary of differentiated bodies. They represent samples of the interfaces within these now destroyed worlds. Together, this collection of meteorites tells a story of a violent, early solar system. Many bodies formed, grew large enough to differentiate, and were then destroyed. The fragments we collect on Earth are scattered samples of these lost worlds. Now let me examine the dynamical evidence for the fifth giant planet. The Nice model, developed in the early 2000s by researchers at the Côte d'Azur Observatory in Nice, France, proposed that the orbits of the giant planets evolved significantly after their initial formation. The model successfully explained several features of our solar system, including the orbits of Trojan asteroids, the structure of the Kuiper belt, and the late heavy bombardment of the inner solar system. But the original Nice model had difficulties. Simulations starting with the 4 giant planets we observe today, often failed to produce the current configuration. The dynamical evolution was too chaotic, sometimes destroying or ejecting planets that we know still exist. To address these difficulties, researchers proposed modifications to the model. One important modification, developed by David Nesverny and colleagues at the Southwest Research Institute, suggests that the early solar system contained an additional ice giant, a 5th giant planet that was ejected during the dynamical instability. This modified model, sometimes called the 5-planet NICE model, or the jumping Jupiter scenario, produces simulations that match the current solar system much more reliably. The additional planet absorbs some of the dynamical instability, taking the gravitational kick that would otherwise have disrupted the surviving planets. The simulations suggest specific properties for this ejected planet. It would have been an ice giant similar to Uranus or Neptune, with a mass of about 10 to 20 Earth masses. It would have originated in the outer solar system, possibly between Saturn and Uranus in the original configuration. During the dynamical instability, it would have been gravitationally perturbed into an unstable orbit and eventually ejected from the solar system. The ejection probably involved a close encounter with Jupiter. As the largest planet, Jupiter has the most gravitational influence, and most ejections in dynamical simulations involve Jupiter as the agent. A close passage near Jupiter would have flung the smaller giant planet outward at high velocity, breaking the gravitational bond with the Sunday. Once ejected, the planet became a rogue wandering through interstellar space without a parent star. It is now somewhere in the galaxy, billions of kilometers from any star, slowly cooling and growing fainter. Could we detect this specific planet? Probably not directly. Rogue planets are extraordinarily difficult to detect because they emit virtually no visible light. They can be found through gravitational microlensing. When they pass in front of background stars, their gravity bends the light slightly, producing a temporary brightening that can be detected. Surveys have found rogue planet candidates through microlensing, and theoretical estimates suggest that the galaxy contains many billions of rogues. But identifying which rogues came from which stars is essentially impossible. Once a planet has been wandering for billions of years, its origin is lost. So the 5th giant planet, if it existed, is somewhere out there but unrecoverable. We can study it only through its effects on the solar system it left behind. Now let me describe the late heavy bombardment and what it tells us. About 4 billion years ago, give or take a few 100 million years, the inner solar system experienced a period of intense impact activity. This late heavy bombardment, LHB, also called the lunar cataclysm, left scars across the surfaces of all the rocky planets and many moons. The evidence for the LHB comes primarily from the moon. Lunar rocks brought back by the Apollo missions show a clustering of impact ages around 3.9 billion years ago. The moon's largest impact basins, including Imbrium, Serenitatis, and Crisium, appear to have formed during this period. Earth surely experienced similar bombardment, but Earth's geological activity has erased most of the evidence. Mars and Mercury show many ancient impact craters, consistent with the LHB hypothesis. Even the icy moons of the outer planets show evidence of intense impact activity around the same time. What caused this bombardment? The leading hypothesis is that it resulted from the dynamical instability of the giant planets. As the giant planets shifted into their current orbits, their changing gravitational influence destabilized the orbits of countless small bodies. Many of these bodies were sent into the inner solar system, where they collided with the rocky planets and moons. The same dynamical instability that ejected the 5th giant planet would have triggered this bombardment. The events are connected. Both are consequences of the same chaotic episode in solar system history. The LHB tells us about the violence of the early solar system. It was not a stable, peaceful environment, but a chaotic and dangerous one. Planets formed, but they did so in conditions where collision and destruction were common. Many bodies that formed did not survive. The planets we see today are the survivors of this dangerous era. For life on Earth, the LHB has important implications. If life existed before the LHB, it would have faced enormous challenges during the bombardment. Some impacts might have boiled away oceans, sterilized continents, or otherwise made the surface inhospitable. The evidence for life on Earth begins shortly after the LHB ended. Whether this is coincidental or causal is debated. Now let me describe the evidence from extrasolar planetary systems. Our solar system is no longer the only one we can study. The discovery of planets around other stars, exoplanets, has revealed a vast diversity of planetary systems. By studying these systems, we can place our own solar system in context and learn about the processes that shape planetary systems generally. Exoplanet observations have revealed several relevant findings. Many planetary systems show evidence of past dynamical instability. Systems with multiple planets often have orbits that suggest violent histories, eccentric orbits, mutual inclinations, planets at unexpected distances from their stars. These features are consistent with episodes of dynamical chaos similar to what may have occurred in our solar system. Hot Jupiter's gas giants in very close orbits around their stars are particularly interesting. These planets cannot have formed where they currently orbit. The conditions there are too hot and the materials too sparse to build giant planets. They must have formed farther out and migrated inward. Some hot Jupiters likely migrated through smooth interactions with the protoplanetary disk, but others appear to have arrived through violent dynamical processes. Planet-planet scattering, in which one giant planet is sent inward while another is ejected, may explain some hot Jupiters. This means that other planetary systems have likely ejected planets, just as our solar system may have. The galaxy is full of rogue planets, many of which were once part of planetary systems before being thrown out by their siblings. Free-floating planets, planets not bound to any star, have been detected through microlensing surveys. Estimates suggest that the galaxy contains as many rogue planets as bound planets, possibly more. The total number of rogue planets in the galaxy may be in the trillions. This statistic underscores how common planet ejection must be. If the galaxy contains trillions of rogue planets, then planet ejection is a routine outcome of planetary system formation. Our solar system, if it ejected one or more planets, is not exceptional. Other planetary systems also show evidence of collisional histories. Some systems have unusual dust distributions that suggest recent collisions between substantial bodies. The Beta Pictoris system, for example, shows evidence of ongoing collisions and may contain a debris field similar to what an early solar system might look like. By comparing our solar system to others, we gain perspective. Our system is not unique, it is one of many. The processes that shaped it, dynamical instabilities, collisions, migrations, ejections, operate throughout the galaxy. Understanding them in our system helps us understand them generally. Now let me describe the specific case of Theia and the moon-forming impact. The moon-forming impact is one of the best studied catastrophic events in solar system history. It occurred about 4.5 billion years ago when a body called Theia, approximately the size of Mars, collided with the